Hello and welcome to another video in this series as we learn the very basics of Lean for writing simple maths proofs. Today we're on the 8th tutorial, and it's actually going to be part of a small set of related videos. So just to put that into context, we'll be doing a series of 4 videos, and I've actually done one already, number 7 and then number 8, and then the next two after that will be 9 and 10. And in the in the 7th one, the last one, we looked at a hypothesis which was disjunctive, was an or, so or hypothesis. And today we're going to be looking at an and hypothesis. So remember, the hypothesis is part of the starting point of a proof, and the conclusion, the proof objective, is where we were trying to get to, so we call that the conclusion or the proof objective. In the videos after this one, we're going to be looking at an or proof objective, and also an and proof objective. So there's the 4 combinations. So we've got hypothesis, and we've got objective, and then we might have or and. So those are the 4 combinations. So we've done that one already, because a proof by cases essentially splits the hypothesis into several pieces, where each of those pieces could be true, at least one of them. So that's that one we did last time. Essentially covers this case, a disjunctive hypothesis. So proof by cases. There we go. Today we're going to be looking at a hypothesis which is conjunctive, and some of these, these 4 scenarios, some of them are more interesting than others. So let's be upfront. The and hypothesis isn't that interesting compared to the others, but we just need to know how to handle it. Similarly, the and objective is also not that interesting compared to the or cases, just because they're simpler and more trivial. But again, we need to know how to handle them. So let's kind of dive in. So just to set out the context there, previously we looked at logical or hypothesis, the proof by cases, and today we're going to be looking at logical and, a conjunctive hypothesis. So here's an example, really simple maths problem. As you know, the idea is to keep the maths simple so we can focus on learning about lean proofs and not get distracted by the maths. So here we're saying, given, so this is the hypothesis, x is 5 and y equals x plus 3. So those are the 2 things we're given, and we need to prove y is 8. Now, without writing code or even pen and paper, you could just look at this and say, well, y equals x plus 3 and x is 5 here, so y is 5 plus 3, y is 8. It is as simple as that. It's not that difficult, but we are using this simple example to learn to see what kind of structure a lean proof has. So just in case you didn't know, I'm sure you did, the symbol, kind of a upward pointing wedge, means logical and a statement of that form, P and Q, means both P and Q are true. If it was a disjunction, like we saw last time, then P or Q means that either or at least one is true. P is true or Q is true, or both are true. So these are called conjunctions, whereas the other ones were called disjunctions. Let's draw a picture just to remind ourselves. So with or, and then we've got and here, the symbol is that one, and here it is that one. And if we say P or Q is true, that means P is true, or Q is true, or P and Q are both true. At least one is true. With this one, we've got P and Q, and they both have to be true. That might be a refresher for many of you who already know this. So we've got a hypothesis of that form, P and Q. So those both statements, P and Q, are both true. Let's go back to it. This statement is true, and this statement is true. It sounds obvious, yes, I know, but the reason we're kind of labouring the point is because we want to eventually translate what we're saying into lean. Now, P is true and Q is true. That's the same as having separate hypotheses P and Q. Again, let's draw a picture. So if I have a hypothesis of the form P and Q, that's the same as having two hypotheses P and Q, because they're both true and they're both true. Once you realize that, then actually we can transform these kind of composite statements into simpler ones. And then we proceed just as we've done for lots of previous examples where we've had either one or more hypotheses. So in that sense, it's not particularly interesting. So I know we've used a lot of words, but essentially that's the crux of it. A hypothesis that's conjunctive, P and Q, is the same as having two hypotheses, a hypothesis P and hypothesis Q. If this was longer, PQR, then we'd have a third hypothesis as well, because all of these are true, and the same as this, all of these are true. So yeah, nothing interesting in that sense, but we need to know how to handle them in lean. So this is the structured proof, which is a little bit laborious, but again, the idea is to get into that frame of thinking so that we can translate this into lean code. So we start off with a given fact, which is that conjunction, the and hypothesis, this and this, a conjunctive hypothesis. Now we're going to split that into two hypotheses. So we've got two derived facts which are both true. X is 5 and y is x plus 3. They're both derived from that. And now we use these as hypotheses and proceed as we've done many times. So the rest of the proof is not new or exciting. It's what we've done lots of times before. It's a calculation essentially. So y is x plus 3 using this derived hypothesis, and we substitute x for 5 using this derived hypothesis, and we end up with 8. So that should not be unfamiliar now, that from here onwards. The only new thing here is splitting a conjunctive hypothesis into separate hypotheses. You can read this in your own time. There's also a blog which chooses the words a little bit more carefully than what I'm doing now. I'm speaking to you off the top of my head. The slides are all online as well if you would find them useful. So here's the lean code, and let's work backwards. So the calculation, the calc section is very, very familiar now. We want to prove something about y. We know it's x plus 3 because of this hypothesis that we've created. We'll come back to how that's created. And then we substituted x, 5 for x, and that was by another hypothesis which we derive here, and then we get 8. So the interesting thing is happening here, and similar to how we split a disjunction, we use the obtain instruction again, but the format is different. So we have these angled brackets and a comma. So a disjunctive hypothesis H, which is this one here, we split it into 2, and because this is a conjunction, we use these symbols. So just a reminder that if we had P or Q, then our obtain instruction would be HA vertical bar HB H. That splits it into two there, into two cases. Whereas here we've got P and Q, and then we use obtain angle bracket HA comma HB angle bracket and the one we're deriving it from. So it's just a different pattern for matching what should be inside H, a disjunction or a conjunction. So that's relatively simple. This is the only new thing, how to split a conjunction into separate statements, both of which are true. You can read this in your own time at a slower pace if you'd like. Let's see what the effect of doing that obtain is. So let's move over to some actual live code. So all this code is online and you can download it from GitHub and work with it yourself and explore it yourself. Here is the example we've just been talking about. So if I put my cursor before obtain, I've got x and y declared as integers. I've got a proof objective of y is 8, and I've got a hypothesis h, which I've declared here, and it says x equals 5 and y is x plus 3, so it's a conjunction. But after the obtain instruction has been complete, if I put my cursor after it, you can see it's split into HA and HB, two hypotheses. So the goal hasn't changed. The variables, of course, haven't changed, but instead of H, we now have HA and HB, and in fact it erases H because these are equivalent. By having these two hypotheses, both of which are true, there's no longer a need for H. So it's equivalent. So I hope that's kind of clear. The rest of it is a simple calc that we've done many times before. Have a go yourself. It's worth kind of playing around with the code and messing it up and seeing, how to fix it, because you learn a lot by doing that. If you want to read more slowly what we've just done with looking before and after the obtain instruction to see the effect on the hypotheses, you can read the slides more slowly. You can download them. So here's a small easy exercise to practice, and it's very similar to the example we've just done. So the idea is to write a lean program to show that y is not equal to 8, but more than or equal to 8, greater than or equal. Here x and y are real numbers, could have been integers, doesn't really make a big difference. And the idea is that our hypothesis is a conjunction. So given what we've just done, you'll be splitting this into two hypotheses. One is a very simple equality, but the other one is an inequality. And you might want to go back to that video where we learned how to work with inequalities in hypotheses, and then to prove a conclusion which is also an inequality. Remember to use the rel tactic as that's just a hint there. So have a go at that. This shouldn't be overly difficult, particularly if you've worked through the previous video on inequalities. If there's any issues, if there's any difficulties, let me know in the comments and we'll have a conversation about that. This video has been kept short because there's not too much to talk about today, and in the next video we'll jump on to disjunctive proof objectives, which are actually interesting, so that one might be a slightly longer video. So we'll see you in that one. Bye.